Talk about the extreme value theorem. And if you are a random person who found this on the internet, you can print a guided notes sheet at this bit.ly link, bit.ly/EVT notes. And let's move on. So there are different types of extrema that we will be talking about. One of them is the absolute, also known as the global max and min. Those are the highest and lowest values over a specific interval. And then there's also a local or a relative max or min, which is the highest or lowest within a small viewing window. A few things about absolute and local extrema is the absolute extrema can occur on the endpoint. So if you have a closed interval defined in the problem, you can consider and you should consider the endpoints for an absolute max or a min. And if you are looking at a problem where an interval is not specified, then it is understood that you are to find the max or min on the entire domain of the function. And then for local extrema or relative extrema, that is the highest or lowest within a small viewing window. And these will not occur on endpoints. That should be endpoints, not endpoint, whatever. Now, I put a little disclaimer on this. This is in the context of AP calculus. There's actually a little bit of disagreement among textbooks about whether or not endpoints can be considered local extrema. And we actually have a disagreement with AP pre-calculus. In AP pre-calculus, endpoints can be local extrema, but in my class and in AP calculus, I will not be including the endpoints. So if you are not one of my students, you'll need to talk to your own teacher or professor about the inclusion of endpoints with local extrema. I will not have local extrema at endpoints. And so we have this little graph down here, and I've added some labels to it, which is not on the sheet that I linked earlier, but let's find the local and absolute extremas. And let's start with absolute. And those are the absolute highest and lowest points on a graph. And so right here at x equals a, we have an absolute max at x equals a. And the max value is whatever y coordinate you achieve. So the maximum is the function's value at x equals a. And so there's your absolute max. The absolute minimum is occurring down here when x, what I'm calling x equals b. So here's my absolute minima at x equals b. And the minimum value is, why did I put a d down there? What am I doing here? That's a holy cow. Okay, hang on. Let me fix these labels. There we go. And so f of b, the y coordinate at b, is your absolute minimum. Now let's talk about local extrema. And the local is if you're looking only in a small viewing window, what is the lowest and highest point? And let's look right here at x equals c. X equals c. This is a local maximum, and I prefer local. Relative is probably used more frequently. But if I cut that little square out of some paper, and I just showed you that little bitty piece, within that small viewing window, that would be the highest point. And so we will call this a local maximum at x equals c. And let's see, is there a local minimum? And there is. And there's a local minimum right here at x equals b. Now, I realize that is also the absolute minimum, but if I did cut that little square out of the paper within that small window, that point at x equals b is still the lowest point in that little local region. And so that is an absolute and a local minimum at x equals b. And then in my class and in AP calculus, d, even though that is the lowest point right there at the end, because it is at the end, the only thing that can be in my class and AP calculus is the absolute max or min. It's not the absolute max because we have points that are higher, and it is not the absolute minimum because we have points that are lower. So that is nothing. That is nothing as far as the local and absolute extrema. Okay, so a few more notes. Let's talk about critical numbers. The word critical has a very specific meaning in calculus, and a critical number is any number where your derivative is equal to c, where your derivative is equal to 0. So x equals c is a critical number of your function f of x if f prime of c equals 0, and that's what most people will think of first. However, places where the derivative fails to exist can be critical numbers as well. Does not exist? Let's change that to does not exist. There we go. So critical numbers, your derivative equals 0 or the derivative fails to exist. And what you have to remember is critical numbers must be in the domain of your function. So if you have, for example, a vertical asymptote at a certain x coordinate, well, if your function does not exist, if there's a vertical asymptote, then the derivative will not exist. That is not a critical number because vertical asymptotes would not be in the domain. The x coordinate would not be in the domain of the function. So make sure critical numbers are in the domain. And then there's this little factoid down here that if a function has a local extrema, so that is a small max or min in a small viewing window, if you have a local extrema at any coordinate, then that x coordinate will be a critical number. So all relative extrema do occur at critical numbers. Keep in mind that the converse of that statement is not necessarily true. If x equals c is a critical number, it may not be a max or a min. It is possible to have critical numbers that are not local extrema. So do not assume every critical number is a local max or a local min. However, every local max or min will be a critical number. And let's put this into practice a little bit, starting by finding critical numbers of these two functions right here. And critical numbers mean you want to find where the derivative is equal to 0 or if the derivative fails to exist. So let's start by finding the derivatives. The first one's going to be really easy. F prime of x is going to be 2x minus 7. I hope that's an easy derivative. And then for critical numbers, we will set 2x minus 7 equal to 0, and we get a critical number of 7/2. And that is in the domain of this function. This is a continuous function. It's a quadratic. That is nice. One thing I would discourage, and I used to do this for a long time. When you find when you're looking for critical numbers, do not put the equals 0 up here on that first line because you're kind of suggesting that the derivative is always equal to 0, which it's not. The derivative is only equal to 0 at a certain point. So a little technicality in the world of AP calculus. Let's find the derivative. Then in a following line, set that derivative equal to 0 and solve. Okay, so let's do this for number 2 as well. F prime, this is a product rule, so it'll be 2x e to the x plus x squared times the derivative of e to the x. Now we need to set that equal to 0 and solve. I will factor out an x and an e to the x. That will leave me with a 2 and an x. I will set that equal to 0. E to the x never equals 0, so I'm not worried about that. However, that x can be 0 on the outside here. 2 plus x will equal 0 when x is negative 2. And there are our two critical numbers of x squared e to the x. Find the derivative, set equal to 0. And there you go. You do want to consider where the derivative fails to exist, but that does not happen in either one of these examples. And I don't think I have an example of that anywhere in this lesson. So let's go on and talk about the actual extreme value theorem. We're finally there. We talked about, I threw the name out there, threw the name out at the beginning of the video. So the extreme value theorem basically says that if your function is continuous, and always pay attention to criteria for any theorem, if your function is continuous, does not have to be differentiable, only continuous, then your function will have an absolute max and an absolute minimum somewhere on the interval. It is possible to have more than one. You could have several. So for example, the graphs of sine and cosine x have absolute maxes at 1, max values of 1 and negative 1 at multiple x coordinates. But you are guaranteed at least one. And we're going to put that in practice down here where we are finding absolute maxes and mins of these functions. And I do give you an interval. And when you are on a given interval, you want to consider the ends, because absolute extrema can occur at the endpoints, and critical numbers. Well, the endpoints are given, so my ends are x equals 0 and x equals 3. So I want to consider those. I also need to find the critical numbers. So to get my critical numbers, we're going to take that function's derivative, which will be 6x minus 12. I will set that equal to 0, and I will have critical number at 2. Then I now need to find out which of those three give me the highest value and the lowest value. And the easiest way to do that is simply to plug them back into the function. Do not plug into the derivative. I want to know the function's actual value at each of these candidates. And some teachers even call this the candidates test, where you find your candidates, your endpoints, and your critical numbers, and then you plug them into your function to see which one returns the highest and lowest value. So f of 0 is 0 minus 0 plus 5. f of 2, 3 times 2 squared would be 12. 12 times 2 is 24. Plus 5, that's negative 12. Plus 5 is negative 7. And f of 3, 3 times 3 squared is 27. 12 times 3 is 36. Plus 5, 27 minus 36 is negative 9. Plus 5 is negative 4. Then we simply look for the highest and lowest values that were returned. My maximum value is 5. So I have a max value of 5. And that max value occurs at x equals 0. And then I have a minimum value of negative 7 at x is equal to 2. And x equals 3, the other end point, is neither the max nor the min. And so we aren't worried about that one. So there's number 1. And I have 3 more examples, and I'm going to go through these a little bit more quickly because I do assume that we know how to find derivatives and set them equal to 0. Once you find the derivative, it's a bunch of algebra, really. The only calculus is that first step where we do the derivative, where we differentiate the equation. So I've gone ahead with number 2. This is a cubic polynomial that will be continuous always. The derivative is this parabola, factor out the 6, factor x squared minus x minus 2, and you get critical numbers of negative 1 and 2. One thing to look out for is to make sure your critical numbers actually fall on the given interval, and both of these do. So now I'm going to test my endpoints and my critical numbers. I need to find f of negative 2. I need to find f of negative 1. I need to find f of 2. And I need to find f of 3. And we will see which one returns the highest and the lowest value. And so if you want to pause the video and work those out by hand, you can. For the sake of speeding this up, I will pause the recording and you will see the values up here in just a second. And here's what I came up with in my head. I may have made an arithmetic error. I probably should have double checked this in a calculator, which I just did. And those are correct. So now I am looking for my highest and lowest. And so my maximum value, max value, is, and the highest value is 8, and that occurs at x equals negative 1. My minimum value is negative 19. Is it 1? Negative 19 at, and that occurred at x equals 2. Okay, so we have 2 more examples, getting slightly more complicated. So here we have a quotient. We're on the interval 0 to 3. Anytime you have variables in the denominator, you want to consider discontinuities. However, x squared plus 4 cannot be 0, so nothing to worry about as far as discontinuities. You will sometimes have a function with a discontinuity that falls outside the specified interval, so something to look for there. I have gone ahead and found the derivative, so if you want to work this out on your own, you have a few seconds, or you can pause it. And there we go. Okay, here it comes. And here is your quotient rule all cleaned up. So I have my derivative down here. Notice that when I set the derivative equal to 0, I dropped the label of f prime simply because I don't want to make that suggestion that the derivative is always equal to 0. We're just finding critical numbers down here. Critical numbers or a fraction will equal 0 when the numerator is 0. So I have critical numbers of negative 2 and 2. And notice that negative 2 is not on the interval. So for this problem, we will toss that one. And for my candidates, I will test f of 0, f of positive 2, and f of 3. I don't think this one will take too long. I'm just going to do this one without pausing the recording. F of 0 is 0 over 4, which is 0. F of 2 is 2 over 2 squared plus 4. 2 over 8 is 1/4. And f of 3 would be 3 over 3 squared is 9 plus 4 is 13. And so my absolute minimum is 0. My minimum value is 0. Well, I'll write it that way. Minimum value is 0. And that occurred at x equals 0. My maximum value, I now need to compare 1/4 and 3/13. And let's see, 1/4 I know is 3/12. And so if I'm comparing 3/12 to 3/13, my higher value of the two will be the one with the smaller denominator. 3 over 12 will be larger than 3/13 if the numerators are the same, a larger denominator creates a smaller value. So I'm going to change that to 1/4. I was going to write 3/12. My max value is 1/4, and that occurs at the x coordinate of 2. And then I have one more example, I believe. And I do. This one looks kind of scary. We have trig functions, which really shouldn't scare you. Just in my experience, I've learned that students do not like those. So let's find the derivative. This is a nice derivative. You should be able to spit this one out fairly quickly. However, solving it may be tricky for you because a lot of students just refuse to learn the unit circle and your common angles in that. We are on the interval 0 to pi over 3, so we're looking squarely in the first quadrant. 0 is here. Pi over 3 is your 60-degree angle up here. And we're looking for a place where cosine minus sine x would equal 0. That is where they are the same, and that occurs at pi over 4. At pi over 4, the coordinates are √2/2 and √2/2. And so I now need to find my function's value at pi over 3. I will start at 0. Function's value at 0, my function's value at pi over 4, and my function's value at the other endpoint of pi over 3. And I'm kind of curious where this is going to go. 0 is going to be convenient because sine of 0 is 0, cosine of 0 is 1, so that's 0 plus 1. Pi over 4 would be √2/2 plus √2/2, which cleans up to simply the square root of 2. Now, I happen to know that the square root of 2 is approximately 1.414. If you didn't know that, you should kind of have an idea of where it might be. Put that in a thought bubble. And then pi over 3, the sine of pi over 3 is √3/2. Cosine of pi over 3 is 1/2. And so that would be the square root of 3 plus 1 divided by 2. And we now need to try to figure out which of those two is higher. Let's see. The square root of 3 is approximately 1.7 plus 1. And if you divide that by 2, that's 2.7 over 2. That's going to be 1.35, which is less than 1.414. And I think that 1.7 is rounded, but even if I did include more decimals, that's not going to be enough to bring this up to 1.4. And so my minimum value is 1, and that occurs at x equals 0. My max value is the square root of 2, and that occurs at x equals pi over 4. And there we have it.